In this AstroPictionary Concept video, we're going to go over stellar blackbody spectrum comparisons. The first spectrum we're going to look at is the sun's spectrum. The sun spectrum is shown by this white line. We are looking at wavelength on the horizontal axis, and we're looking at what's called irradiance on the vertical axis. On the horizontal axis, let's start by looking at wavelength. Notice that we see this red, orange, yellow, green, blue, indigo, violet. That's our V band. And our red is on the right side and our violet's on the left side. To the right of red is the infrared band, and to the left of violet is the ultraviolet band. So we can see that wavelength increases to the right. Let's look at irradiance now. Irradiance is going to increase in the vertical direction. Irradiance is the power, which is watts, being emitted at the surface of an object, in this case a star. So it's watts being emitted per meter squared at a particular wavelength. So what we do is when we want to get the spectrum of a star, we start quantifying in different wavelength bands. So we measure how much power is being emitted per meter squared from the sun at a wavelength of 1800, and we just put an X. Let's go to 1200. We find out how much it is, and we put an X. At 900, we put an X. 600, we put an X. And at 400, we put an X. Same thing with 500. And 5777, we put an X, and the same thing at 300. And then what we do is we draw a line through it, and the perfectly smooth line that we draw is called a blackbody spectrum. So here you see blackbody is at 577 Kelvin and is colored gray. Everything underneath the curve is called the blackbody. Now notice that the sun is not a perfect black body. If you take a look at it, you see that we have these white lines all over the place. Those white lines are absorption lines. They're chunks taken out of the black body spectrum. So the sun's photosphere, the lower part, has this black body spectrum, and then the upper layers are cooler, and so those upper gaseous layers absorb some of the light coming from underneath, and you see these chunks taken out at different wavelengths. So we see an absorption spectrum. So the sun is not a perfect black body. Let's take a comparison of different stars at different wavelengths along with some planets. Once again, we are looking at wavelength increasing to the right. If you notice, we have the same violet on the left and red on the right of the V band. So therefore infrared is to the right and to the left is UV. Once again, we're looking at radiance or irradiance on the vertical axis, and it's increasing upwards. Once again, we have watts per meter squared. So how much power is being emitted at the surface of the object per meter squared at a particular wavelength. And we can do the same thing. We can quantify them, but notice that all the shapes are the same. We're not showing absorption spectrums in these particular examples. We're only showing the perfectly smooth curve of the blackbody spectrum. And remember, the area under the curve is that blackbody spectrum. Notice we have different surface temperatures of objects. We've got an object at 100 Kelvin at its surface, 300 Kelvin, 500 Kelvin, 1000 Kelvin, 3000 Kelvin. Here's the sun's at 5777 Kelvin and at 10,000 Kelvin. Let's take a look at each of these spectrum. Let's take a look at the 100 Kelvin. Notice that the 100 Kelvin surface object has this blackbody shape, and none of this blackbody shape is crossing this Roy G. Biv line. Therefore, this object that has a surface temperature of 100 Kelvin is not emitting in the UV or in the V band. It's only emitting in the infrared. So an object that has a surface temperature of 100 Kelvin, you would not be able to see any visible light coming from it because it doesn't emit any visible light. It only emits infrared light. Same thing with the 300 Kelvin object. None of it crosses the Roy G. Biv, so once again, it's only emitting in the infrared. Same thing with the 500 Kelvin object. It's only emitting in the infrared. It's only when we get to this 1,000 temperature object, 1,000 Kelvin temperature object, that we see part of the curve crossing into the red portion, yellow, and then greens. So we notice that the red portion, how much this star emits red light compared to how much this star emits at green light, is much greater of the red light than the green light. So we will generally see this star as the red color, but it still also emits mainly in the infrared band. So it does emit some visible light, and we will generally see it as this color red. Let's take a look at the 3,000 Kelvin object. The 3,000 Kelvin object emits a lot of red and a fair amount of green, but not so much on the blue side. Blue is a lot less. And once you get down to violet, violet is even less. But the point is, the 3,000 Kelvin object emits red, orange, yellow, green, blue, indigo, violet. It emits not only in the infrared band, but it also emits in the V band, the entire V band, compared to the 1,000 Kelvin object that emitted no blue or violet light. And this 3,000 Kelvin object also emits in the UV band. Let's go take a look at the sun. The sun also emits in the UV band. It emits across the entire V band spectrum, and it also emits in the infrared light. Notice the peak color of the sun. The peak color of the sun is in the green. So if we had to classify the sun as a color based on its peak, we would call the sun a green star because it emits mostly green light of the Roy G. Biv rainbow of colors. Let's go take a look at the 10,000 Kelvin object. The 10,000 Kelvin object emits mostly violet light of the red, orange, yellow, green, blue, indigo, violet. It emits less red light than it does violet light. Therefore, you would see this star as violet. You would see the 1,000 Kelvin surface star as red, and you would see the 10,000 or even higher temperature surface star as the color violet because it emits more violet than any other visible band. It also emits in the UV, and it also emits in the infrared. So let's take a look at what the trends we see here. We see this Stefan-Boltzmann trends. We see two trends of the Stefan-Boltzmann law. The first one we see is as temperature goes up, we see that the curve increases. We see a lot more black body spectrum as the temperature goes up. So what we see is a higher amount of power being emitted per meter squared with the higher temperature object. So you can see this in the Stefan-Boltzmann law, that as the temperature goes up, the luminosity, which is your power, goes way up. Notice temperature is to the fourth power, so luminosity is going to go way up. The 10,000 Kelvin surface object is very luminous compared to the 1,000 Kelvin surface object. So that's one property of the Stefan-Boltzmann law. The other property of the Stefan-Boltzmann law is that we're going to look at the colors. We notice that as the temperatures go up from 1,000 to 10,000, the stars appear more blue or more violet. At 1000 Kelvin, we don't have any blue colors being emitted from the surface of the star. But at 577 Kelvin, we have some blue light being emitted from the star. And at 10,000 Kelvin, the star is mostly emitting blue or violet light. So we see this increase in the amount of blue light being emitted as the temperature goes up for stars. So the second property of the Stefan-Boltzmann law that we see looking at this graph is that the hotter the star, the bluer the star. So two trends that we see. Hot stars are bright. So the hotter the star, the brighter the star. That's your luminosity. The second thing that we see is that the hotter the star, the bluer the star. And I'll put proportional to blue here. So it's indicating that the hotter the star, the bluer the star. So these are the two trends that you see with the Stefan-Boltzmann law and the comparison of these black body spectrum.